Hello, Mr. T here with our final video lesson on our conics units, and this will discuss conics translations. Up till now we have focused on conics that have been centered at the origin or have the vertex of a parabola at the origin, and now we want to shift those to other places in the coordinate plane. Translations refers to a process of shifting some base function, and we've used that repeatedly this year for all the different function families we've explored. If you remember from doing this from earlier functions, we've had frequently a number in a parentheses next to the x that has caused a horizontal shift, and numbers added or subtracted to the y that have caused it to be shifted vertically. For conics, we'll be focusing on finding the center of the translated shape, and we will call that coordinates of that center h and k, so we'll be using the letters h and k for our horizontal and vertical shift. And just a note, for parabolas, they don't have a center, so we'll be focusing on the vertex. Let's look at the translations of the standard forms of the equations. On this chart, I'm just going to be showing the horizontal versions of the various shapes. You'll be able to figure out the equivalent for the vertical because you'll see a repeating pattern here. So to translate our parabola to a vertex of hk, we just subtract h in a parentheses next to the x and subtract k in the parentheses next to the y. As we go through the other shapes, the pattern will be exactly the same in all cases. So you might want to be writing down these standard forms of our translated conics, and you may want to add for the parabola, ellipse, and hyperbola the vertical versions of those. So let's go through a couple examples of graphing these conics. In the circles unit, we already talked about translating the circle, so we'll go through examples of the other conics here today. So let's start with this first example. We can see here as our equation, and since we only have one letter squared, that tells me that this is a parabola. To put it in standard form, we just need to do one thing here. We need to split this number into 4 times p. So let's factor out a 4. So we get 4 times negative 3. So our p is negative 3, which is one of the key parameters for a parabola, if you remember back to our unit on parabolas. So as we said, we have a parabola. Since the y is the letter squared, it tells me it's horizontal. This is x minus h, so h is 1. That's our x-coordinate of the vertex. If we put this in the form of y minus k, we would need k to be a negative 2. So we're always going to be taking the opposite of these numbers. Parabolas are symmetrical, and this is horizontal, so the line y equals negative 2 is our line of symmetry. And we'll be using p to find the focus and directrix. So let's plot the parabola. I started with my vertex here. Now p was negative, so that takes us to the focus, so I went 3 units to the left since p was negative. If p had been positive, we would have gone to the right. On the other side, we have 3 units our directrix. I've shown our line of symmetry here, and if you remember on graphing parabolas, we can get 2 other points by going parallel to the directrix through the focus, 2p units, so 6 units up in this case, and 6 units down to get additional points so that we can sketch our parabola. Let's look at another one. Okay, what shape is this one? Okay, we have equals 1 and a plus here, so that tells me this is an ellipse. Since we have the bigger number under the y, it tells us it's a vertical ellipse. So let's look at breaking this down. So we've already talked about how we determined it was an ellipse and vertical. Again, we take the opposite of the number with the x, so we get positive 3, and here the opposite is negative 2. That's our center of our ellipse. This is our a squared, so square root of that's 6. This is our b squared, 5. So to graph it, since we're going vertical, we go a units up and down to get to our vertices, and b units right and left to get to our co-vertices. At that point, we could draw the ellipse. Frequently we'll be asked to show the foci also. So to find the foci we need to find c. And if you remember from the unit on ellipses, our equation is c squared equals a squared minus b squared. So to find c, I'm going to have to take the square root of that quantity, and we get 3.3. And the foci are on the same axis with the vertices, the major axis, so I go up about 3.3 and down 3.3 to get my foci. Let's look at one more. Okay, this looks a lot like the last problem, except now we have a minus here, so that it means this will be a hyperbola. And this time it's going to be not vertical, but it's going to be horizontal, because the way we decide vertical, horizontal on the hyperbola is by which letter is positive, and in this case the x is positive. If you don't remember these rules that I've been talking about graphing the basic conics, you should go back and watch the unit on each particular conic and then come back to our translations. This will be our a squared, so a is 5, our b squared, so we take square root, we get 6. For this one, to find where the foci are, we use c squared equals a squared plus b squared and take the square root. Our center, the opposite here, is 3 and negative 2. So again, to sketch a hyperbola, we start with the center. We find our vertices, so we're going horizontal a units and b units. And we put the other side of our bounding box by going up and down b. Now remember, we draw this bounding box. This is just a tool to sketch our final hyperbola. It's not part of our graph. Diagonally through the corners of our bounding box are our asymptotes. And once we have our vertices, our bounding box, and the asymptotes, we can sketch in our hyperbola. And I also showed here using our c value, our foci. The hyperbola always wrap around the foci. So now we've taken ones in standard form and graphed them. Let's talk about how we can, given key information from a conic, write its equation in standard form. So I've got 3 problems here. We'll go through each one. So our first one's dealing with an ellipse, and we're given the vertices and the covertices. Key thing here is our center is going to be the midpoint between the vertices and the midpoint between the covertices. We could use our midpoint formula and just find the midpoint between these points. I did the midpoint, or halfway between the x's on the vertices and the y's on the covertices. You'll also notice a pattern on ellipses where the 2 points that have common y's, that will be the y coordinate of the center, and these 2 points have common x's. That number will also be the x coordinate of the center. Sorry. So we have a center at 3, 2. Now we need to figure out our a value. If you remember from ellipses, the distance between the 2 vertices is 2 times a. So if we find the distance between these 2 points, now we could use the full distance formula, but since they are horizontal to each other, we can just subtract the x coordinates to get 2 times a. So I have to divide that by 2. So my a is 6. And likewise, half the distance between the covertices is our b. And now we can just plug into the template. X minus h, h was 3, y minus k, and I'm missing a squared here, sorry. That should be a squared, I'll fix that. And we have, since it's horizontal, because these are side by side, we put the a squared under the x and the b squared under the y. Again, there should be a square symbol here. Let's look at number 2, a hyperbola. In this case, our vertices and our foci all line up. Foci and vertices all line up on a vertical line. They all share the same x-coordinate, so they're vertical from one another, so we have a vertical hyperbola. Halfway between the vertices or halfway between the foci, either one, is going to be the center. So our center is going to be at 2 for h, because everything's along the line x equals 2. And we take halfway between the y values, and we also get 2. So our center is at 2, 2. Again, like on the ellipse, our foci is the distance between the foci are 2 times c. So if we take half that distance, we get our c, and half the distance between the vertices is a. We need b to write the equation, so we use our equation here for hyperbola of c squared equals a squared plus b squared, and solve for b, and we get b squared 7. We don't need to take the square root because we're going to put b squared in our form. And unfortunately here I've made the same mistake. This should be a 2 here. And we have, since it's vertical, the y is positive, the x is negative. We put the a under the positive value, and again we have y minus k and x minus h, and they're always equal to 1 on hyperbola. Okay, finally our parabola. Our vertex and foci line up again on a vertical line because they have the same x values. So we can find our value of p. P is the distance between the vertex and the focus. So we go up 8 units to get to our focus, so that means it's vertical since we went up. And the coordinates of the vertex are our h and k, and now we plug into our template. Since it's vertical, the x is squared. And we can just simplify the 4 times 8. If you're having difficulty determining whether these are horizontal or vertical, just sketch a quick graph and plot these points and determine whether they are lined up in a vertical pattern or a horizontal. So if you can't visualize it just by in your head, go ahead and sketch a graph. Now in this unit we need to be able to recognize conics, and in a second we'll be talking about conics that are not in standard form. So we've got some rules here about how we can determine whether a equation of a conic is which particular shape. Parabolas are easy to find. It's the only conic that has only one squared term. So if both the x and the y's are squared, then it can't be a parabola. To distinguish between circles, ellipses, and hyperbolas, we need to look at the coefficients of the x squared term and the y squared term. If the x squared and y squared have exactly the same coefficient, both number-wise and sign-wise, it's a circle. If they both have different coefficients but they are the same sign, either both positive or both negative, it's an ellipse. And finally, if the terms are different, the coefficients are different, but have opposite signs, it's a hyperbola. So let's practice this on our next slide. So think about which conic each of these is. Can't be a parabola because we've got 2 letters squared. So now we need to focus in on our coefficients of the x and the y. Since they're different, it's not a circle. They're both positive, so that means this one is an ellipse. What about here? Okay, again, it's not a parabola. We have 2 things squared. It's not a circle because this number and this number are not identical. And this one's positive and this one's negative, so that means this one must be a hyperbola. This one should be easy to find. We only have 1 letter squared, so it's a parabola. And finally, the last one. A little tricky because we've got 4 and 4, and if you look too quickly, we might think this is a circle. But notice we have minus here and positive, so this is actually a hyperbola. These equations are in what are called a quadratic or a polynomial form. These are not standard form. So the last part of our conics unit is we might want to be able to find the center of this ellipse and the values for a and b so that we can quickly sketch the graph. So we're going to be talking in this last part of the unit, how do we put an equation that's in these forms into standard form. So we just went through this, what shape does this make, and we should see that we have the same coefficients on our 2 squared versions. So this is a circle. But now we might want to know what is its center and what's its radius. To accomplish that, we're going to be using something called completing the square, which we used back in our unit on quadratics as a mechanism for solving quadratics, or by putting a quadratic into vertex form. Just a quick refresher on the completing the square topic. We are trying to take two terms of a trinomial, so the terms that have the x's, and we're trying to add a constant term that turn it into something called a perfect square trinomial. Perfect square trinomials factor into x plus or minus some number squared, and that's the template or the form that we're looking for in our standard form of the conics, because we want x minus h squared. The pattern is we take the coefficient of the x term, divide it by 2, and square it. So if we add that to our trinomial, that turns it into a perfect square trinomial. And when we factor it, the number that goes in the parentheses for the factor is just that coefficient divided by 2. So if we look at these examples down here, half of this plus 2 squared would be 1. And half of this coefficient is 1. So when we square it, that would turn into x plus 1 squared. Half of this is negative 6. If we square that, we get 36. And when we factor it, we would have x minus 6 squared. And here we're going to get a fraction. Half of that is 3 halves. So if you square 3 halves, we get 9 fourths. And if we factored it, we would have 3 halves. So we're going to be using this completing the square actually twice on a circle, because we have to complete the square for the x terms and the y terms. So this is the problem we have from a couple slides ago. We want to be able to find our center and our radius. So our first step will be to group the x terms and the y terms together and move any constant to the right side of the equation. So I've reordered this. Addition is commutative, so we can move our terms around. And now we have to complete the square on this portion and this portion, so we have to complete the square twice. Remember, we'll look at this number and take half of it and square that number and add to both sides of the equation, because this is an equation, we need to keep it balanced, and we have to do the same thing on the y. So we complete the square on the x, we complete the square on the y, and we add the matching terms to the other side of the equation. We now factor each of these trinomials. Remember, this is going to factor into x, and then the number that's going to go here is going to be half of this number, so minus 2. Same with the y. And over here we just calculate that, and we got 16. And now it clearly looks like the circle that we're used to. And we can tell that our center is at 2, 3. Remember, we take the opposite of these numbers. And this is r squared, so we take the square root and we get the radius. You've now successfully at least watched and hopefully completed our unit on conics, and hopefully you'll have success completing our applications and problems in class and on your unit tests. So good luck.